So good afternoon, everybody. It's a pleasure to be here. Our first time on the Linux Developer Conference. I'll be talking a little bit about malware, malicious software, in this case distributed in ELF binaries. Just to make clear, this is not a presentation about the Linux kernel, but about the whole Linux stack, all the ecosystem, all tools that you probably have been used to. This is also a talk specifically about development, but how about the tools that you have been developed can be abused, tampered, and subverted by malware, right? So before I forget, I'm Marcos. I'm a computer engineer and master in computer science by Unicamp. There are a lot of guys from Unicamp here. Good to see everybody again. Currently, I'm a PhD student from Federal University of Paraná. A lot of people here, they brought the code here, so thank you.
Hi everyone, I'm Lucas. I'm a computer engineering student at Unicamp. I've been analyzing ELF binaries since 2016. It's going to be 3 years now in October. I'm going to start introducing our course. It's going to be a two-part presentation. The first part, we're going to talk about the technical tools for reverse engineering. And the second part, we're going to talk about Linux malware landscape. Before I start talking about the technical tools, we're going to start giving a little motivation about why we study malware in Linux environment. Most people, most users believe that malware is strictly Windows related and that it's not present in any other operating system. However, that is not true. Malware is present in essentially every operating system, essentially Linux as well. And since Linux is so diverse and it's been growing, it's more present that it's getting a lot more presence nowadays. So yes, Linux malware is a real threat. I'll start with 3 examples. The first is about the Erebus ransomware. So in 2017, during the ransomware growth, we had WannaCry for Windows. We also had Erebus for the Linux system. So Erebus would attack Linux servers at the time. Especially, it took a South Korean network provider called Nayana, and it encrypted all its servers, about 150 servers, and demanded $1 million ransom. Nayana did pay for these, for the keys, but never received any of them. So they lost all the data. A second sample is Hidden Wasp. Hidden Wasp is a lot more newer. It's from May of this year. It's still being analyzed because it's very special. It barely uses any new source code. So generally, malware are present in families, and inside these families, they use the same libraries, they use similar functions, they reuse code. Hidden Wasp, on the other hand, barely uses any old code. It's basically new source code. So it makes it really hard for AV companies to actually detect it. And it's been used in targeted attacks where the malware developer actually knows who he wants to attack, sends over Hidden Wasp, and takes remote control, like a backdoor, of everything that the user is doing. And one more example about Golang malware. So Golang malware are malware that are written in the Go language. Go language was developed by Google in about 2009. So it's 10 years old. It's very new. And because it's very new, very few people have been developing in this language. And because very few people have been developing this language, antivirus companies have a hard time as well detecting this code. So malware developers have been using Golang malware more and more frequently since 2018. And they've been using it for ad campaigns or crypto mining campaigns.
So our goal in this presentation is try to spot this malware and try to understand what they have been doing, try to get some insights to provide feedback to make you aware of what's happening. So the first task is try to define malware, which is very hard. So in this presentation, we define malware in terms of behaviors. So some of these behaviors might be present on benign software individually, but what characterizes a malware is that basically they make only malicious behavior. So here we have a very short taxonomy of some function calls or API calls that are related to some malicious behavior. So for instance, we have network-related malicious behaviors that are implemented by API calls and system calls related to network, like socket. Not because the socket system call itself, but because it's used by malware and abused by malware. So for instance, malware used the network to spread its payload, to scan the network, to spread its malicious payloads, to download the other payloads from the internet. as well as for the other ones. So for instance, we have the evasion behavior, is like a malicious process abusing the kill system call to terminate other process, like terminating an AV, terminating a firewall, dropping a policy, and do this kind of stuff. The same for evidence removal, like trying to delete a log or to deleting a user file, or even modularity, for instance, implement a lot of forks. Not about the fork system call itself, there's nothing wrong with the fork system call, but the problem is that the fork can be abused by a malicious actor. Like in the past, malware implemented fork bomb, exhausting all system resource, and currently malware deploying many processes from the initial one, dropping many other processes and forking a lot, trying to spread its payload among multiple processes in order to make a detection harder. So in this presentation, we'll talk a little bit about all these behaviors using the system calls and function calls as proxy for identify the malicious behavior. So to make you understand a little bit more this abstract concept of malicious behavior, I'll present some examples. So for instance, we have a network scanner. This is part of a log that we collect in our firewall. We have here a malicious process that's basically a scanner. So you can notice that consecutive IP addresses are contacted in the same time. That's basically because this malicious process is scanning the whole network in which it's connected. So basically, it starts scanning, and it finds a vulnerability, it drops its payloads there. Another example here, it's part of a dump of malicious files. If you interpret the strings, you can notice that basically it has a lot of IP tables, packet filter strings, that basically set the packet filter off or drop the policy or even shut down the service. So basically, it's an evasive behavior implemented by this malware. Another example is Terminator. Basically, this process is trying to terminate another process that's blocking its execution, and their implementation is varied a lot. So basically, he can try to invoke a shell and try to kill all the process, or even directly invoking the kill system call on a non-PID that could be, for instance, the firewall, the antivirus, and whatever, and trying to terminate this process. And the final example, this is the modular malware. So basically, each time the malware is invoked, it is invoked to use a distinct parameter, a distinct command line. So basically, each time the process is invoked, it's performing a single step of an infection. It's very hard to be detected because each one of these executions is not malicious itself, but when you combine all the actions, it's made malicious, it makes some harm to the system. So this is the kind of all behaviors you are trying to detect and spot and tell you how prevalent this behavior are in malicious binaries. So basically, to do that, we inspect binaries, either look into the binaries or trying to execute the binaries somewhere and look what happens. But this task is not so straightforward as it looks like, because attackers are completely aware that someone you try to reverse engineer the samples, and they implement anti-analysis techniques. So they implement countermeasures to our analysis. So we have to be smart enough to try to analyze the samples. Basically, when you try to analyze malware, you have two approaches that are statically and dynamic analysis. The static analysis, basically, you look into the binary without executing it and check what you get. So basically, you have been using the tools that you probably are familiar to, like file, strings, object dump, try to identify what happens. But if it's useful when you are debugging your benign binaries, it's not true when you are analyzing malware, because malware, you try to obfuscate its content. So if you look into a binary, you note basically an obfuscated string, a compressed string, an encrypted string. Sometimes the strings are not static, but runtime generated. So the malicious strings won't appear when you run the binary, which makes analysis harder. So a popular obfuscation techniques, for instance, is packing. That basically consists in embedding your malicious binary into another binary, which is a compressor. So if you inspect this binary, you are in fact inspect the compressor, not the malicious payload. So this is because it's hard to analyze malware. So we have to move to another approach, in this case, that are basically dynamic analysis, where when we run the samples on a controlled environment that we call sandbox, it's network isolated, so basically a virtual machine that we are running all the samples that we present here. So you have control, and you trace all the samples, like you use the tools that you probably know, like ltrace, strace, ptrace, and whatever, and try to analyze what we get dynamically. Again, this is not so trivial, it's not straightforward, because attackers are aware that we will try to trace them, and you implement countermeasure to tracing. So for instance, if you try to trace a binary, an attacker might try to implement some static compilation approach to defeat the analysis. The same for strace. Since strace is based on the ptrace framework, the attacker might try to detect the ptrace framework and avoid executing. So it executes in the victim machine, the attacked machine, but will not execute in the attacker machine, which is very hard. It's not trivial as tracing a benign malware, a benign binary. And even try to implement some more advanced techniques like rootkit techniques. So to make it clear, we'll show some examples.
So I'm actually going to do a hands-on presentation and show a few malicious samples and how they behave. So I'm going to start off. Now I have to hold this, so bear with me. Showing a non-obfuscated sample. So I have it right over here. And if I try to see the strings of this sample, this will tell me a little bit about the sample. Now we can take a look, and we can say everything that is contained in the sample. As you can see right over here, you have some browser user agents over here. So you have a lot of the information about what this malware will actually do. You have some browser user agent information over here. So if you actually take a look and take more time to actually analyze this, you can have at least an understanding of what this sample might try to do. However, malicious samples don't usually come like that. They'll try to obfuscate. One way they can obfuscate is, like Marcus said, through packing. So we have a packed malware over here. I'm going to show it's packed with UPX. So as you can see, it's packed. And if we try to perform the same command, the strings command, you're going to see that it'll have a couple of strings saying that it's UPX, but most of the other strings, they're all encrypted, and they're not legible, humanly legible. They don't mean anything because they're a compressed file. So this is one of the ways that malware can evade static analysis. Now most samples, they do something else. They try to compile the samples statically. And when they do that, they'll take all their libraries and put it there with them. It is also great for the malware because, first, it's an obfuscation technique, but also it's a way for a malware to take all the libraries and all its dependencies with them to the infected system. When you see all these, and I'm going to show you that it's very common, all these samples right over here, they're all statically linked. So this is a very common tendency among malware developers, and you only have essentially one loss, which is the growth of the sample. So it's going to be physically a lot heavier because it's going to have all the dependencies with them. If I try to do a dynamic execution, that's why I'm going to do this in a virtual machine. It's network isolated. It won't run through ltrace. So this is an evasion technique that the samples will use. So it's a great win situation for the samples. Now, there are other evasion techniques that the samples can do. One of them is called ptrace. So most of the trace solutions use this ptrace system call, which means that they're going to say who they want to trace. However, only one person can trace a process at a time to not have any conflicts. However, the strace solution, the tool is already analyzing the sample. If the actual sample tries to pretrace itself, thank you. If the sample actually tries to do pretrace on itself, and I'm going to show it to you, and we're going to use -f to follow the sons. We're not going to talk about all fork systems here. As you can see, it tried to do a ptrace trace me. And what happened is it managed to see that it was not permitted. And usually it's supposed to be permitted. So it knows it's being probably analyzed. So it's going to kill itself. And then it's going to wait. And it's going to wait essentially forever. So this is another evasion technique that the samples can use. One more evasion technique that the samples can use is to essentially make analysis impossible by making the analyst wait for a very long time. What that means is, if I put the sample over here, it's just going to be dormant. And it's going to be dormant for a very long time, much longer than analysis, but shorter enough so that it can take like a few days, and then it will start injecting the payload. But the analyst doesn't have a few days. So what we can do is we can inject code into this malware and actually make that sleep function go away. One way we can do that is through LD preload. I have a function over here called sleep. It's got the same signature as the sleep function. However, it returns 0. So no matter how long this malware wants to wait for, it's going to return really quickly. So if by any chance I got my makefile over here so I can have a cheat sheet of this copy. It will not wait in the sleep anymore. Now in this case it failed to execute, but at least it passed that step. So we can just keep analyzing it more and more and try to understand what it's going to do. However, this preload technique can also be used by the malware developers. Essentially any tool that the analyst has, the developer also has. They're all for open source tools. So they're going to make use of them. And they're going to know and they're going to use anti-analysis techniques. One of them is a rootkit. So a rootkit essentially is a piece of the malware that can do some malicious execution. As you can see, I just did ls, and you see a malware right over here. So let's suppose that is your malicious tool. Now, if I run this way, if I run this rootkit, the malware is gone. However, this is the first type. This is a very simple rootkit where we only disabled the printing function. So in this case over here, you have a problem because I'm only disabling the printing function. However, malware can be a little bit more intelligent than this, and they can do, so I have an LS over here. This is going to be a little bit different. Now it's completely gone. So what I did in this case, instead of just disabling the printing function, I actually disabled the file. So the file, when ls tries to read this file, it's not there anymore. So this can be even improved more and more by a malicious developer. They can also use it for the PS call. And this is going to be my last example. In this case, if I press PS, you're going to see all the processes that are currently working. If I grep for bash, I should see that bash is working. However, I do this, and I grep for bash on the malicious system. You're going to see that bash is gone. So, malware, thank you very much. So malware can make use of a lot of these rootkits and a lot of other things to make essentially it disappear or try to exploit any other bugs. And now I'm going to keep going to the second part of the presentation for the purpose of time. The second part of the presentation is we applied all the techniques that we saw right now to actual malware, to actual Linux malware. To do that, we required a very large data set, and we got that through two repositories, VirusTotal and VirusShare. In total, we managed to get 5,600 malware samples. Now, the thing we see about malware in Linux environments is the architecture heterogeneity. So we have several types of architectures for the Linux environment, and essentially like everyone here develops for some sort of Linux architecture, so do malware developers. So they'll develop malware for every one of these architectures. The most famous, most present one is still the x86, simply because it has so many users and servers and everything like that. We also have a great presence of ARM, especially due to Android systems and other type of Linux ARM systems. But if we compare what we have of our data sets to even newer data sets that are coming out today and every other day, we see that the embedded systems and the other systems have gained a lot of the market share. So they're growing, and malware developers are making use of this. So they can attack different systems. So what we started by doing is we performed a static analysis on our samples, so we can essentially know, without executing the samples, what they were supposed to do. So the first tool that we used was object dump for disassembly. Now, many of the samples, they try to obfuscate static analysis, and that's what happened in this case. Many of the architectures are even supported by the tool yet. But from the samples that we were able to analyze and actually take information out, we managed to take out several functions and system calls from these samples. Now, they're all separated into their architectures because they're all so different. So depending on what architecture you're going to be, you're going to have different types of malware behaviors. However, one behavior that is very common among all the architectures is the network usage. So when we do a disassembly, we see a lot of network-related functions, socket and connect. Now, as Marcus said, socket and connect are not malicious by itself, but they can be used in malicious ways. So our next step was to analyze network strings. So we used the same strings command that I showed in the presentation, the hands-on part, to collect email, URL, and IP addresses. Now again, these are not malicious by itself, but when used by a malware, they can be used to download a malicious payload or upload information from the user. So that's why malicious developers use it so much. So as you can see, at least 40% of the samples, and I say at least because we cannot confirm that through static analysis. We can try to confirm that through dynamic analysis. We get that malwares use a lot of the network, and they use a lot of network strings to actually do that. So these are the strings that are actually hard-coded into the malware text. They could have some that are obfuscated, or they could have some that are runtime generated, and we wouldn't know at static analysis at this moment. One of the obfuscation techniques that I said was packing. So we made an analysis on UPX packing on our samples, and we saw that several of the samples were packed with UPX. There are other packers they could have used, and other techniques as well, or even obfuscate the use of packers, and we wouldn't know. Many of the samples that were not packed can be explained through the labels contained in their antivirus labels. So many antivirus companies, they already had these samples, and they categorize it. They give it a label. What type of malware is it? Is it a virus? Is it a Trojan horse? Whatever it is. In most of our cases, they were exploits. And that explains a lot why many of our samples were not packed. Because exploits, they're usually not malicious by themselves. They'll use a bug, they'll use an exploit to execute their malicious payload. We also had rootkits, many of them generated by LD preload, as mentioned before. And since most of our malware was contained, 60% of our malware were contained into only 3 categories. They're probably very much related. So what we did is we did a malware family analysis, which is, if they're related, they're probably going to have some code or a lot of code related to each other. So we got our samples, and we tried to determine which malware is at least 90% similar to another malware in our data set. And what we got is this clustering technique. So most of our samples, they were actually present in a cluster of around 2 to 5 samples. Most of them were present in this range. However, we had clusters of malware that had 91 samples. So that means 91 samples that are at least 90% similar to each other. In this case, if they're very similar, they change maybe a couple functions, maybe some IPs or something like that, just so it can continue to be very similar and not be, but still different, so AVs won't detect them. However, everything that I said in static analysis is only a lower bound. We cannot be 100% sure that that will actually happen, but we can perform dynamic analysis with a lot more mindset on what we have to do. Dynamic analysis will actually have to execute the samples. And executing malicious samples is not like executing benign samples, essentially because they carry a malicious payload. They'll try to infect your system. So we had to do it in a very safe environment. So we used virtual machines, we isolated the network, we had firewalls on, we had traces, we had a lot of systems going on. But we still had 2 problems. The first was, even though we execute these samples, they still won't stop executions by themselves. They're not going to let go of execution. So we had to actually terminate these samples and run them for only an amount of time. Another problem is some samples, they depend on very specific conditions to be executed. For example, the Erebus ransomware requires it to be a Linux server to be infected. If it's not a Linux server, it's not going to have a malicious execution. Instead, it's just going to terminate itself. So many of these samples require several libs or something else, and if they don't have it, they'll just terminate. That's why many of the samples actually compile statically, because they'll always have these dependencies with them. We only executed the x86 samples on our server simply because executing all of them would require a lot of systems. Okay, so we took all the samples and we did the same functional analysis that we did for the static part. However, in this case, we had a much more thorough understanding of what we had in the data because it's going to be a lot more realistic. We see that the network data still maintained. About 50% of the samples still did network usage. As you can see, we also have two types of data. One is the x86 64 bits, and the other is the 32 bits. So the 64 bits are believed to be a lot newer, and the 32 bits are believed to be older. And we can see there's a big difference on the techniques used by the malware. The 64-bit samples, they use a lot more of the resources in Linux instead of the 32 bits, simply because they have to be more and more thorough because analysts are coming more for them. We also see a great rise in modularity. So most of the malware, they'll try to use modularity. They'll use fork, they'll use any sort of system that will modify itself. We access through dynamic analysis, we could know essentially where all the samples would try to access. We see password and chattel files, which is likely a very malicious behavior. We also saw them trying to tamper with configuration files and the -proc directory. Another interesting thing about Linux malware compared to any other, for example, Windows malware, is the social engineering feat. So in Windows, you have a lot of the social engineering malware that will try to make you click a button, talk to you, and make you do an action. However, in Linux, that really doesn't happen. First, the Linux user is a lot more aware of its environment and knows a lot more how to actually act in these situations, but also because Linux has a lot of servers that are not actually manually controlled. Instead, they are just left there and automatically controlled. Therefore, the malware will have to use, instead of social engineering techniques, they'll have to use actual evasion and attack techniques. Amongst the evasion techniques, we have fork, which was mentioned, preload, ptrace, sleep, and most of our samples would use at least one of these evasion techniques, if not all of them. The network traffic, we also were able to analyze the network traffic to the firewall logs, and we can see that most of our samples would try to actually use the network. Some of them would just fail because the network wasn't available, but some would just keep trying. Many of them were also scanners. They would try to scan all the network, or at least the local network. And by scanning the local network, we see a great rise in the .br domain. So among the domains, there is a predominance among global domains, which is expected, but the local domains can only be explained by the use of scanners. Now, everything that we said here can be used on the detection of malicious samples. So by using all the techniques and all the data that we gathered, we were able to actually construct an antivirus based on machine learning. And with those data, we were able to feed it to a machine learning algorithm, to an array. For example, how many times did the sample do fork? How many network strings are present in that sample? And compare those to a benign sample. So we use benign samples from the Linux systems, from the user bin and the bin directory, and we compared those to all our samples. And we were capable of getting, with the random forest algorithm, accuracy of over 99%. Why is that meaningful? Because it shows that what we're doing as an analysis is actually working. So we can actually analyze malicious samples. Furthermore, not only can we analyze and get great accuracy results, we can actually get feedback on our samples. We can get feedback from the machine learning algorithm and say which features that we pass to it are relevant and which are not. So network strings that I've been mentioning a lot is because it is very, very useful to classify the samples. However, password strings, that even though seems like a very great malicious execution, is not that much. But it's still malicious.
Yeah, in our lab we have a long-term research line on malware. So we have been performing this kind of large-scale malware analysis, longitudinal studies on malware. So we have data to compare the Linux malware to other ecosystems. So in this case, I will present a comparison of the Linux dataset I have presented before and the Windows dataset of malware collected in the internet of Brazil in the last years. So it's interesting to notice that if we look to Linux labels, we have a lot of exploits. And this can be explained basically by the fact that Linux, the greatest market share of Linux is on servers and the other autonomous systems, so it doesn't require a lot of user interaction. So they basically are trying to exploit remote machines. But if we change to the Windows scenario, we have the opposite. So if we look at labels, we have very few rootkits and very few exploits and a lot of, for instance, of PSW, that's basically password stealers. So basically the software that's aimed to collect users' data. That's because the Windows market share is basically on home user, on desktop machines. So when we're analyzing Linux and Windows malware, it's not only a matter of porting a malware from a Windows executable to a Linux executable, but also understand how the ecosystem changes. So the approaches that the attackers will tackle in the both environments are different, and our strategy as defender must also be different. Another example, so we haven't seen that for Linux we have some ptrace. It's a non-negligible number, but not so that significant, and a lot some UPX malware. But if we look to the Windows one, we have the opposite. Like for instance, packing is the most popular technique. Like most than 50% of Windows malware is using packing. That's because in Windows they are self-contained binaries that need to be protected, and when they are on Linux they are exploited. So the target is another process, not the exploiter itself. And also for debugging. So whereas 10% of the Linux malware is using a ptrace technique, an anti-debug technique in Windows is the second most popular one. So it's a very widespread technique. So it shows again that analyzing malware in different ecosystems is not only a matter of changing the technique, but changing the context, changing the whole behavior of attackers, users, and also of defenders. Finally, I would like to show some case studies of interesting stuff that we found whereas we have been analyzing these samples. The first one is an SSH backdoor. This is a typical case where even a benign software can be considered malicious if used out of its original scope. So it's hard to say that, but kind of drawback of it being something open source is that the source is available to everyone to use, in the sense that malicious actors you also use, not only us as a professionals and so on. So nothing prevents an attacker to download the source code of SSH server, recompile it in a malicious payload, and distribute it. So basically what this sample does is to recompile, repackage, distribute. So if you got infected by this SSH backdoor, it will open a high port backdoor that's not the 22 as usual, drops the malicious attacker private key there, and you are basically having a backdoor on your system using the legitimate SSH server. So if we trace that, we can see exactly the moment where the attacker drops its public key on the infected server. And it's basically only a recompiled version of a SSH server with some add-ons to infect the machine, right? And also the same for ransomware. Lucas mentioned a few times the Erebus ransomware. Erebus is a very popular trend on Windows, but we can also find a ransomware in Linux. So in this case, the Erebus is our one. It basically encrypts all user files and notifies an attacker using a Tor network, and basically demands for ransom, presenting a Bitcoin wallet, so we have to pay the ransom there. If we look to the trace of this ransomware, we notice basically all this behavior, the attacking drop its key, the attacker form building in runtime that string that basically it's the IP address of the command and control. And they are also building in runtime the hidden service and the onion address of the attacker. And basically after that, the machine is completely compromised. All files are encrypted. So basically, going to conclusions, I expect that we can have presented you at least a little bit of what is considered malware on Linux, give you some insights what's considered malicious behavior. Hope we have shown you that the threat of Linux malware is real, so we should protect ourselves, we should develop a better software, and hope that the insights we provided here might help you somehow. It's very interesting to notice that analyzing this kind of malware can provide us feedback messages. So basically, if we have here network admins, so you have a bigger problem because Linux malware is basically focused on network. And also, of course, that the difference between Linux and Windows, so each ecosystem has its own characteristics, so it has to be approached on distinct ways. We have published an academic paper about that, so you can find basically all these results in a much more detailed way. We have a white paper in the GitHub. We have some scripts there you can find there. Even if you are interested in taking a look at all these samples that we presented here, basically get in touch. We'll be around. So thank you, everybody.
Thank you. Any questions?
Hi. What are the current persistent techniques these malwares were using that you analyze? Another question. I'm not sure how old or how new these malware samples were. When you applied your algorithm, your machine learning algorithm, if you applied them on newer malware.
It's a mix. The first data set starts collecting data in 2007, and the last one ends in 2017. So it's basically we have 10 years of malware collection. It's more than 5,000 samples. So basically we have all the Linux malware ever developed. So it's a mix. What about persistence? I don't know if I get it exactly right, but if you mean surviving reboots or something like that, it's very interesting because it's very different from Windows to Linux again. Because on Windows you have an end user machine that you basically be rebooted, you basically shut it off and unplug it from the energy, and you enter in the deadlock, blue screen, all this kind of stuff of Windows. And basically it shut down a lot, and Windows malware has to survive reboots, basically write to the run registry key. In Linux, it's basically the opposite, since they are basically targeting servers. Servers have very high uptime, so basically they are not trying to surviving a lot. So it's almost negligible the rate of samples doing that. When they do that, basically they set up themselves in the initd to survive reboots.
Well, we are finishing now this session. We are over the time. Applaud for our speakers and have a good afternoon.